And welcome back. And so our next panel, one I'm really looking forward to, talking about Artemis 3. You know, when we first returned to the moon, I think currently scheduled for 2025, and how that mission and subsequent missions will actually help lead us feed forward to Mars. So this is very exciting because we're finally getting back into deep space. We're going to get back to the moon, and hopefully we'll be on Mars in the 2030s at some point. So leading this panel, moderating it, is Beth Mund. Beth has been a longtime friend of our organization. She's a former NASA spokesperson, an analog astronaut. Many of you know her because she's the host of the podcast Casual Space, but she also has this great new project called Stories of Space, the Stories of Space Project, when you're sending stories of people into space. And I know you have some updates on that. So, ladies and gentlemen, Beth Mund.
All right, good morning. I'm very excited to introduce this next panel for you. Please welcome Dr. Masaki Fujimoto. He's the Deputy Director General of the Institute of Space and Astronautical Sciences from JAXA. Next is Shatel Bhakta. He is the ESDMD Strategy and Architectural Office and Lunar Architectural Team Lead at NASA. Ben Talman is the Senior Astrodynamics and Satellite Navigation Engineer and Project Lead from Advanced Space. Welcome, Ben. Joe Cassady is the Executive Director of Space at Aerojet Rocketdyne. And finally, the Senior Director and Program Development of Civil and National Security Space from SpaceX, Nick Cummings. So as we mentioned, this is an exciting panel because as we get Artemis ready to take us to the moon and on our lunar surface, this is going to be a fantastic opportunity for us to look at how we're going to do this as well with Mars. So Dr. Fujimoto, if you'd like to get us started, and we're ready.
Right, thank you. Yes, let me try to explain what JAXA does in moon exploration and Mars exploration. If I could have the slide. Yes, so this describes lunar exploration and Mars exploration. So let me start with the manned mission, the lunar manned mission. First, we will send a rover to the southern polar region for the resource prospect purpose. And this is like a 300 kilogram-ish small rover. But then eventually, our plan is to develop and then send this relatively large rover, manned pressurized rover, to the surface of the moon. This is our direct contribution to the Artemis program. And it is the size of the weight of this rover is like 11 tons. And so it's a large rover. And the plan is to let this run in the polar region of like over 100 kilometers or something. That's the range we have, or even 1,000 kilometers. That's the range they have, the human exploration people have in their mind. But that's the story from the JAXA human exploration people. But I myself is from the Science Institute within the agency. And we were when we learned about their program, I realized that most of the missions they have in their mind is relatively large, and you cannot do this so frequently. But when it comes to the lunar exploration, lunar surface exploration, maybe it's nice to have a program that develops technology for OK-sized missions. So yeah, that's the plan. And actually, we will have a small lander for a tech demonstration. We will demonstrate the pinpoint landing. The landing ellipse is like 100 meters, not kilometers, 100 meters. So it's relatively precise. And then it's going to have a two-stage scheme for landing, so that you can see in this graphics that it's not really standing on the surface. It's kind of clinching onto the surface, which means that you can land on a slope region. So pinpoint landing to a slope region that is of high interest in science. This technology will enable such an exploration, and by a small asset. And then starting from this slim pinpoint landing technology, we were thinking about having a tech demo program for OK-sized exploration. But it's a tech demo, but at the same time, we think it should be driven by 9 top science themes because we are from the Science Institute. And we do have picked up 3 top science themes, like radio astronomy on the far side, lunar seismology network, and then the sample return. Of course, we do not complete all of these big science themes. We are trying to trigger, we are trying to take the first step towards these big goals, and eventually, through a synergy with the larger missions or maybe manned missions, we will complete this science exploration. So that's the story we have in our mind. And once we have this, OK-sized assets that's been proven on the surface of the moon, we can move on to the Mars exploration. So our Mars exploration, it starts with MMX, sample return mission from Phobos, not the moon, not the Mars itself, but from Phobos, one of the Martian moons. And then we are having JAXA Mars landing program in our mind. But this is the concept, but we're building this. And there will be a feed from the lunar exploration, as I mentioned. And we hope that this Mars landing mission of JAXA will be established by providing a common asset for deep space exploration as well. So we take this as a nice trigger so that we will reformulate the way we do the deep space exploration in general and make the deep space exploration program in a more efficient way, more sustainable way. And how do I think? How dare I think I have a chance of establishing this program? Am I going to do something what NASA has done already in a miserably smaller scale? That's not the plan. And because we are now really interested in a lightweight access to the surface of Mars. We're not giving up the limitation we have. I think we should think that all we can do is send something like a 200 kilogram-ish rover to the surface of Mars, which is small, but still you can do a lot if you think about the synergy with the bigger missions or human exploration. So sending a small asset to the surface of Mars, if you concentrate on that concept, we have a nice technology, inflatable soft aeroshell. And with this nice technology we think we are taking the lead. I think we can develop this Mars landing program into the future with support from the lunar exploration. So that's all I have to say. Thank you very much.
All right, thank you. If you could bring up my slides. So I'm Shatel Bhakta with ESDMD. I'm the lead lunar architect. We'll go to the next slide. So our deep space exploration priorities. You've heard Mr. Cabana talk about why we're doing this and what we hope to achieve with the lunar missions and use them as a stepping stone to get to our Mars missions. The benefits to humanity, why we're exploring, leadership, economy, human condition. These 3 pillars between science, national posture, and inspiration lead us to that. So this is the why we're going to the moon and to continue on to Mars. Our strategy and objectives, as was presented here. The objectives are on the right. The QR code was given earlier. But as you see, there's some goals and objectives. They fall under 4 main categories. Accomplishing that, we're hoping to develop the architecture with inputs from industry as well as international partners. And so the objectives here get refined. We make use cases and functions and hopefully develop a framework that allows us to achieve the objectives that have been laid out, or at least nearly achieve them. And so we've got objectives and goals that have been given to us at the agency level, and the teams are working now to develop characteristics and needs, the functions and use cases that make them accomplishable, and that way we can actually achieve looking at it from the end state. There's various end states that we're trying to achieve. There's no one given architecture or manifest that we're trying to get to. And so if you're used to seeing, objectives and then seeing actual, rockets and this specific rover, you're probably not going to see that in the near term coming out of the architecture results that we see. We're trying to keep it open allowing for more collaboration, more integration of different assets. And so that pushes us to be more integrated, more interoperable. As you can see, even within NASA, on the graphic on the right there, along the left, you've got the different directorates within NASA that all feed into the different Moon to Mars objectives. So it's not just the human aspect, like was just mentioned earlier, right? It's a synergistic approach. Smaller precursor missions, robotic missions, human-robotic interactions all need to happen, all focused, around the different objectives, pulling in science, technology demonstrators, as well as how do we do the operations differently. So it's not as narrow focused as we may have been in the past. We're trying to really open the net a little bit and make sure that we're doing something that engages the entire globe. In order to make sure that that continues happening, internally we do the architecture concept reviews. So this would basically be a yearly review. We held our first one just at the beginning of this year, and in the future we'll be holding them in November. The ADD will be the product of that, and those will be released publicly. The first one was dropped, and there'll be a QR code at the end, and so you can take a look at where we're at in the agency and what we're looking to head to. Right now, the why we explore, we've got the why. We've got the science, the inspiration, and the national posture. And so the rest of the questions is what we're trying to evaluate and architect systems around. And so what are the capabilities that are needed in order to be open and expandable? What should the systems be and where they should be? And then how will we get there and how will we return? And then as a means to measure, how well do we approach getting to those objectives? Now, really appropriate to the panel that we're just about to have is the segments, right? Right now, we basically are in the human lunar return segment of the architecture. We've got 4 other segments: foundational exploration, sustained lunar evolution, and humans to Mars. And so as we move forward, none of these are time phase explicitly. They overlap. There's interactions between them. But the intent is foundational exploration builds on what we're doing now. With returning humans to the moon on Artemis 3, and then we'll slowly build our capabilities with contributions from our international partners, industry as well, and then sustained lunar evolution gets us to a larger campaign, things that we find as we grow and explore more of the moon, what more we can utilize in a sustainable manner, and then use those both segments to kind of as stepping stones to get us to Mars. So what can we test out? What can we learn? And what differences that we can accommodate for and head out to our next destination? Some of the systems that you know of, have heard of as part of the human lunar return segment there, just to kind of give you an idea of what we talk about when we talk about this segment. And then an overview. And like I mentioned, this is an overview, even though it does show specific concepts. That's all these are. These are concepts for the different elements. We're not saying that, we want for the Mars terrain vehicle for it to have 2 specific solar arrays. It's just a concept that the teams are looking at. But as you see across the top, we've got the Earth analogs and the LEO analogs. Human lunar return that we're in currently, and as we're trying to ramp up the foundational exploration and the SLE segments, we'll be starting the human to Mars segment as well. So as you can see, they overlap. ADD, some of the products that come with it, and then some of the areas for collaboration. So as you can see, there's quite a few areas that everyone can engage in, and in order to get feedback on that, we will be hosting workshops as well as conferences like this to get feedback. So please feel free to reach out to myself and anybody else from the Strategy and Architecture Office within ESDMD that you see walking around. And then definitely we've got the website and there's emails there as well. So we're on our way, and QR code for the actual ADD and the products that came out with it. So I'll stay there for a second while I pass it on.
Well done. Helpful. As we bring up your slides, Ben, I want to remind everyone, if you have some notes or some thoughts, we're going to do our best to make sure we open it up to questions right afterwards. So make sure you're checking those and keeping note, and then we'll have some time. Go ahead, Ben.
Here we go. So hi, my name's Ben Tatman. I'm with Advanced Space. I'm the navigation lead there. And Advanced Space as a company exists to enable the sustainable exploration, development, and settlement of space. Some of our core competencies at Advanced Space are flight dynamics, software technology development, and rapid turnkey missions. And so I want to get right into one of our key missions. Capstone is a pathfinder for the Artemis program, and it's specifically investigating the NRHO orbit that the Gateway will be flying and testing out some critical navigation technologies. And here's a video of the successful launch, which was in June of last year. And it arrived in its lunar orbit in the NRHO in November of last year. And it's actually carrying out its primary mission right now. So getting to the moon, Capstone's transfer orbit is called a ballistic lunar transfer, and this is a low-cost, low delta-V transfer. The way it does that is you raise your apogee out to 1 to 2 million kilometers, and the solar gravity is dominant, and it changes some of your orbit parameters for you, raising the perigee and modifying the inclination with no cost of fuel. And so then you drift back down to the moon with less cost, but it is a longer duration transfer. And Advanced Space has ton of expertise in this area. We've done a ton of analysis, including designing the Capstone orbit, as well as work for the Artemis program. And it's being considered as a transfer for the Gateway and for other Artemis missions. And then, so going into operating at the moon, the NRHO orbit, which you can see here, is, as I said, going to be the Gateway orbit. Advanced Space does a ton of work with the Artemis team, with the Gateway team, analyzing the NRHO. Some of the benefits of the NRHO are coverage of the lunar South Pole region, which is going to be the site for some future Artemis missions, as well as communications links to the Earth, and there are some station keeping benefits and eclipse benefits as well. So one technology that's flying on board Capstone that'd be pretty important for Artemis and future Mars missions would be CAPS, which is the Cislunar Autonomous Positioning System. So by doing relative radio navigation tracking between two satellites, one of them in sort of a Lagrange point orbit, you can actually get absolute states for both of them with no ground tracking or with limited ground tracking. So that's going to be really critical for enabling more autonomy in the lunar system and in the Martian system. And so we're actually carrying out CAPS tests right now. That's part of Capstone's mission. And so I just wanted to highlight, thinking about going from the moon to Mars, we're looking at technology development, but we're also thinking about operations planning and long-term living in space environments and more. And that's all critical lessons learned that we can take from the moon to Mars. And then just to share some of Advanced Space expertise in Mars specifically, we're supporting UC Berkeley on the ESCAPADE mission, which is actually a 2-satellite formation, the first ever going to Mars. It's going to be looking at the Martian atmosphere. We also have experience with some Martian orbiters that are exploring Martian moons as well, launched in 2020. So yeah, that's all I have.
All right. so to start off my talk, if I could bring up mine and just go ahead and play the video. I'm going to take you back to a night last November, or an early morning, really. Hopefully many of you were there, but for those of you who weren't, maybe we can relive some of the excitement.
Lift off of Orion on its maiden voyage to the moon. And here we go.
Those are our RS-25 engines on the bottom down there.
7, 6, 5, 4-stage engine start. 3, 2,
We were right next door to those young
Boosters
students
ignition.
we were watching.
And liftoff of Artemis 1.
And
We
day
rise
definitely
together
turned to
back
night.
to the moon
Or night
and
turned to day,
beyond.
I mean. It was super exciting.
We are all part of something incredibly special, the first launch of Artemis.
Solids falling off. We burn 8 minutes. That's the jettison motor taking away the escape tower, which we build also. And then the GoPro cameras were just amazing on this flight. Those are our R4Ds firing there as we separated from the ICPS. European Service Module, view of the Earth, going back 50 years since we'd seen that. And these are just some awesome images from those GoPros. I feel like these are the images that people returning from Mars are going to see as you break your way around the limb of the moon and see the Earth again coming home. It's kind of like making that final turn off the interstate when you've been on a 500-mile journey and you know you're almost there.
The Orion spacecraft is barreling its way back home after circumnavigating the moon and
This was the
beyond
big
in
thing
an
here,
elliptical
test the heat
distant
shield.
retrograde orbit. Splashdown. Orion back on Earth.
So that was very exciting to see that all go off so smoothly and so well. And of course, since that, lots of data has been poured over and analyzed, and so far so good. Things are looking really well in terms of being ready for the crew now on the Artemis 2 mission. Let's go to the next slide. So we talked a little bit in the previous talks, and you heard Bob Cabana also mention it this morning about all the various elements that are necessary. And this chart is really a great one, I think, because on that Artemis 1 flight, we essentially checked the box off on a lot of risk reduction on everything to the left there, the first 4 boxes. We're moving toward, and Nick's going to, I'm sure, talk about human landing system. We'll get down to the surface, do the surface mobility, surface ops. Obviously, we have to have different spacesuits that we're getting ready. A really key part is going to be gateway. And at about Artemis 4, we're going to start putting people into orbit around the moon in the NRHO orbit that Ben just referred to. Truly a deep space environment. And, when we did Apollo, we weren't out there very long. We only had, a few days at a time when people were actually out beyond the Van Allen belts. And so we're going to learn a lot when we get out there and stay out there for, days and days at a time, 30-day missions, things like that. And then obviously we'll build up a capability on the surface down there on the lunar South Pole, the Artemis Base Camp. But it's super exciting to know that we're actually building and flying hardware. We're on our way already. So let's go to the next chart. I couldn't resist throwing this one in again. That's what 8.8 million pounds of thrust looks like at liftoff. It was truly, truly awesome to see that all come together and work the way we expected it to. Let's go to the next chart. And just to give you an idea, and I brought my cheat sheet on this one because I want to make sure, when you hear the program numbers and things like that, and you saw some of the discussion earlier, Bob Cabana mentioned the importance of budgets and keeping things rolling. We got a supply chain up and running now. We are working to keep these things rolling. And it's not like one mission per year. You hear, well, they're going to fly once a year. We're working on hardware all the way out through 5 right now. So when you see those budget numbers, it's not associated with a single mission. It's all of this stuff. The Artemis 2 engines there on that chart are done. They're being installed any day now on the core stage for 2. Artemis 3, those engines are all complete and in the barn. The Artemis 4 engines are nearly complete. Now, obviously, all of those were veteran engines from the Space Shuttle program that we repurposed for this, did some redesign. The really cool thing about them is we're now running at 111% versus 104% on the shuttle. And some of you, my favorite quote is taken from Spinal Tap, ours go to 111. So that's obviously new for our Artemis 5 and beyond engines. We're certifying those engines right now. We've brought in a lot of modern technology like additive manufacturing that's going to make those more affordable and easier to produce. And some of that Artemis 5 hardware is actually being built right now. So some of the combustion chamber and manifolding you can see there on the chart is in work right now. So it's just part of the idea that, you know, we are taking these steps and we're making progress toward that goal of getting to Mars. And just to show you one more quick video here, this is one of our engine cert tests that we just did down at Stennis Space Center in Mississippi. You can go ahead and roll the video. And maybe I can do it. Oop, nope, that's okay. It just showed the engine gimbling if you actually played the video. But that's what an RS-25 on the test stand looks like. And you can see the extremely clean exhaust coming out of there. Just burning hydrogen and oxygen and making nothing but beautiful steam. All right, let's go to the last chart and just leave you with the thought that we are on our way, we're just getting started, but a lot of the hardware that we need to take people out beyond low Earth orbit and explore deep space is coming together right now. Thank you.
Okay. All right. Hi, everybody. Nick Cummings. I've only got one chart. I'll try to catch us up a little bit here on time. I work for SpaceX. I was, among other things, I was responsible for putting together our approach for the NASA Human Landing System program with Starship. Now I'm focused on figuring out how we build from that first human landing system mission and eventually get people to Mars, hopefully lots of people. So it seemed appropriate to talk on this panel. A few weeks ago, we had our first integrated flight test of the Starship Super Heavy launch system. You can see there in the image. This is a really, really important test for us. We gathered a ton of data, everything from the launch operations, launch countdown, tanking, with just massive amounts of cryogenic liquid oxygen and liquid methane through launch, liftoff environments, tank pressurization, which was done on this rocket a little bit differently than most other rockets that are flying, so got a lot of data on that. So really an exciting flight. We've got several more super heavy boosters and Starships in production. I think we've built over 200 Raptor engines now, so just a tremendous amount of hardware, and we're really excited to get to our next flight test here shortly. We have, as others have said, we are going to be using Starship to land people on the moon on the Artemis 3 mission. That's our contribution. I think Bob kind of alluded to probably not thinking that's what a lunar lander would normally look like, this enormous rocket that lands vertically on the moon, like something out of Marvin the Martian or something like that. Starship is designed to do a lot of things. First of all, it's a fully reusable super heavy lift launch system. And putting all of those words together is kind of crazy. It's pretty hard to build a super heavy lift launch system. Nobody has ever built a fully reusable launch system before, and so we decided to put those things together and try to do something that's really on the edge of what's achievable in terms of humanity's aerospace capabilities right now. So we're really excited to be a part of that. And to be contributing that to Artemis and to a lot of other missions. So for the Artemis 3 mission, Starship is going to land a couple of people on the surface of the moon. It's going to take people from Gateway or from Orion in the near rectilinear halo orbit that we were talking about earlier, down to the surface of the moon. Starship is, a large vehicle for that purpose, but the intent is to actually prove the capability to take lots and lots of people to the moon, and hundreds and eventually thousands and even hundreds of thousands of tons of cargo to the moon and Mars. That's fundamentally what Starship is designed to enable. So to give you a sense of scale, I was just in our crew cabin, the Starship lunar lander crew cabin mock-up in California, I think it was last week. And the crew deck of the Starship lunar lander is about twice the size of this stage. And there's room in Starship for multiple crew decks. We only really need one for the Artemis 3 mission. Below that crew deck, there are 2 airlocks that are each about the pressurized volume of a Dragon capsule. So each airlock has about the space of a human spaceflight that's flying people to space station right now. Human spaceflight vehicle is flying people to space station now. And then those airlocks are inside a very large garage, which is, again, about double the size of the stage. So the idea is that we're starting with the capability that we need for Artemis 3, and then we'll work towards being able to fly more people for longer durations, adding the ability to land on Mars with the Martian atmosphere, which is a little bit different than landing on the moon where there is no atmosphere. And so that's how all of these things kind of work together to enable a day where we have, ideally, hopefully in our vision, hundreds, thousands, maybe even one day, 100,000 or more people living on Mars. So it starts with this flight test that we had a few weeks ago, and there's a lot more to come. So we're excited. As Bob was saying earlier, it's a really, really cool time to be working in the space program. It's a really exciting time for all of us. So that's all I have.
Yes, thank you. Fantastic. That's really wonderful. All this information and the details, it's just so fantastic. It gets so exciting. I'm going to start off with a few questions, but first I want to just wrap up to summarize what I think I heard, that Nick, there's plenty of room for all of us in this audience to go to Mars.
That's right.
With a space like that, that's very exciting. And by the way, especially for the students and folks, there's lots of NASA acronyms and other acronyms and lots of information we've presented here. Don't be shy. Ask us in the hallway, because this is what we work in, and these are the systems we love to talk about. I know we're not shy. I mean, 2 of us are wearing Planet socks today, so I love them. And so please come ask us, because we love to engage. So let's start off with some questions, and then I'll open it up, and as you have yours, give us a few minutes, and then we'll open it up for your questions as well with the 2 microphones that you see on each side of the auditorium. Let's start off with just this general question. What are some of the things that are definitely going to be much harder when we go to Mars than when we're going to land on the moon? That will be a challenge you're building into your systems, or some of the architects. Anyone want to start with this very...
Sure, at risk of offending my Mars architecture colleagues, but a couple of things are definitely the entry, descent, and landing is different. Nick mentioned the atmosphere, right? Obviously terrain. So at a high level, those 3 things are definitely some of the big ones. There's obviously others as far as infrastructure, but those are some of the starting points that would cause some difficulties or differences between what we'd experience on the lunar surface or Mars.
Yeah, and the time too, right? So one of the great things about testing out human missions in deep space, one of the great things about going to the moon is you're usually only a few days, maybe a couple weeks away from home, depending on what your architecture is. At Mars, you're committed to being gone for a while. So you have to be able to take a lot of equipment and infrastructure. You need to be able to pre and place infrastructure, and you need to take a lot of equipment with you to survive there, because you're pretty much committed to, maybe a 2-year mission, maybe more, maybe a little bit less depending on the architecture. The atmosphere is a little bit of an impediment. It makes things a little bit harder, but it's also a huge asset. So that is probably, a lot of times where there's challenges, there's opportunities, right? So on the moon, we have to propulsively land, which means we have to take all the fuel that we're going to need to slow down and land on the moon. At Mars, we can actually use the atmosphere to bleed off an enormous percentage of the overall energy that you take during transit there. So you don't have to take all that extra fuel that you would need. You just need a little bit of fuel so that you can actually land on the moon. And then, of course, you need some fuel to come home. But there's ways to actually make that there at Mars. So, it's interesting to think about when there's challenges, there's also opportunities, right?
Dr. Fujimoto, you mentioned also weight in your presentation. Is that something that will drastically be affecting how we plan for Mars?
Yes, I think, before you send a human, you better learn a lot. You better learn enough. And that's why we care about the frequency, And when it comes, if you don't have a frequent missions, it's better to be, or realistically, it has to be okay sized. So that's what we are aiming at. And we happen to have the technology to bring the lightweight asset to the surface of Mars, because Mars environment, it's a tenuous atmosphere. You don't have to worry too much about the heating while you do the EDL, but you have to slow down in the tenuous atmosphere. Then you need a big shell to slow it down, but don't have to worry too much about the heating. So we haven't have that technology. And I think Mars landing is everybody's interested in. Everybody has some technology to contribute, but not everybody can create the whole package. So hopefully we'll try to establish the way of performing a lightweight mission to the surface of Mars and get the international partners together, especially the smaller countries who hasn't had the chance to, but maybe we can provide a chance in the future.
Yeah, the other one I think that you have to mention with Mars relative to the moon, and hopefully we'll learn a little bit about the better comms, because one of the things we're going to deal with is the latency problem, and you won't have the real-time communications like we have today with space station. So if you do have a problem on the vehicle or something like that, you can't call down to mission control and get the team in the back room working on it real time. You can let them know, and maybe 15 minutes later, they'll get the message, and 15 minutes later, they'll tell you they're working on it. So you're dealing with that kind of a lag in your communications. You've got to think about how you put a lot more autonomy in the vehicle, and then built in to crew training and things like that to be able to deal with problems on board the vehicle.
Let's talk a little bit about some of the communication challenges, specifically when it comes to the architectural way that we're going to be able to communicate. Let's talk a little bit about what's going to dictate those and help us get through those challenges. So we have, NASA's got the Deep Space Network, but what are some other things that we'd love to make sure that communication runs effectively, smoothly? Because just being an analog astronaut, simulating a Mars delay is very challenging. It's horrific. It's like you're waiting for mission control to give you some feedback or some numbers and data, and that wait is just, you've already done other things, you want to move things. We know with the rovers how this works with the delay. So what do we want to make sure we build into those architectural designs?
Yeah, so as he was saying, with the one-way light time, in addition to that, you have the free space loss. So if you're sending a radio signal, you're going to need a much bigger antenna. You also have the problem of the solar conjunctions. When Mars is on the other side of the sun, there's limited ability to have reliable communications. So some of the infrastructure we could be putting in, for instance, a relay, maybe at one of the Lagrange points, when the Sun-Earth or Sun-Mars Lagrange points, to act as a relay to have continuous communications with Mars. When there's humans there, even during the solar conjunction could be critical. Additionally, you could have other architectural elements like stationary satellites at Mars that have continuous coverage of the surface, and then have sort of a hub satellite that has a a bigger optical high data rate link that can send back data and talk to all of the different surface assets at the same time, providing them with a big antenna so they don't have to all bring their own high-powered radio or optical link to talk back to Earth.
Yeah, I think that's a good point Ben makes, is laser comm is going to be really critical. Just the sheer volume of data that we're trying to deal with. Even on Artemis 1, we were swamping Deep Space Network. I think we were kicking off lots of other people who weren't too happy with us when we were trying to get the data down. So when you're dealing with human missions, just the volume of data you got to get back is a lot higher than what we've dealt with before in our robotic exploration.
Well, what a great segue into the Gateway program and how they're going to use their communication systems and how we're going to use that as a case study for landing. Does anyone want to talk about how Gateway, what are some of the lessons that we're going to be looking at very closely when we apply them to our Mars landings?
Sure. So one of the things you mentioned was that lag time. So one thing that we can definitely use Gateway for is a real-time scenario of that lag, right? If you're doing surface operations from Martian orbit, you can simulate that. Some of the assets are intended to be precursors, right? The rovers are intended to be kind of like the grandfathers or the fathers, and they evolve into what we would hopefully put onto the Martian surface. So some of the same type of analogs that you've participated in would be something we'd be able to use the Gateway for in order to mimic that opportunity, as well as test out systems like, conceptually there's the TransHab. And so if you have the habitation module and the transportation module all coupled, you could put it through kind of a checkout and then stage from there as well.
Definitely. Yeah, and I think back to the analog idea, and one of the things we've kicked around at some of our workshops within Explore Mars is the idea that you could even couple that with surface missions to simulate the effectiveness of crew after deconditioning for a long time in microgravity. What's it like, even though it's only 1/6 gravity, not 1/3 like Mars, you still could do some work toward, predicting what that is going to be like for those crew after they get to Mars after 6 or 8 months.
Getting to Mars is going to be the victory, and then being physically capable to go out and get started on Mars is going to be certainly the challenge. So let's talk a little bit about that. But when Robert Cabana was discussing earlier, he said that humans are so effective. The rovers are fantastic, and humans are effective. I love that, and that we've already traveled the distance on Mars that Apollo has. So fantastic. How are we going to be working with robots? How do you each see how this is going to be such a fantastic partnership?
Well, I love the point you made earlier about a day when we could all go to Mars, right? And I think that's something that we'd love to see happen too, right? I don't think everybody's necessarily going to want to go to Mars, but we would love to create a future where everybody who wants to go to Mars could. I think our space program, our nation's space program, is something that belongs to all of us, and I think that we should all be able to see ourselves in it. And so I think the robotic aspect of it is, if you are going to build a lot of infrastructure for a lot of people, there's a lot of Martian soil that you're going to have to be moving around. There's a lot of infrastructure that you're going to have to pre in place. There's a lot of habitats that you're going to have to connect. There's probably nuclear reactors that have to be maintained. There's a lot of stuff that has to go on the surface to build effectively, a base camp and then maybe one day a city. And humans are going to do a lot of that work, like they have on the International Space Station, in terms of building and maintaining the International Space Station. But I think we need to take another step function forward in terms of how much of that work can be done by robotic assets, either while humans are there, being teleoperated by humans that are there on the surface, or maybe even, it's not an or, and also having a lot of that work done ahead of time so that things are prepared when the people get there.
Perfect. Anyone else? Let's open it up to some questions as we continue to comment. If you'd like to ask a question, go ahead and stand near the microphone, and then when you're right there and we can hear you, we'd love to hear your questions. So please proceed if you'd like. Otherwise, getting back, I'd love to ask each of you too, the Legolith on the moon versus the Mars surface. do we think, I'm so excited for the sample return and when we're going to finally have that to really examine and look at, what do you expect to see and what do you expect to think that we might have to adapt to once we get that sample?
Well,
it's exciting.
I'll throw something out. We're probably not the best panel for that question, but just looking at rovers and the experience we've had, and then of course knowing what we know about the lunar dust, dust is always a problem. It's going to get into gears. It's going to get into things that you don't want it to get into and cause problems. The lunar regolith seems to have that jagged characteristic to it, so it's especially problematic in that respect. Maybe especially for humans if you were to inhale it and things like that. But I would say with Mars that you have the additional complication of dust in the atmosphere and of dust mobility, and what we've seen on rovers, the ability of that then to cover surfaces like solar arrays, which leads us to Nick's comment about needing nuclear power. So, I'll amplify the comment that Bob Cabana made earlier too about we need nuclear power. We definitely need nuclear power to go explore these places. And my example I always love to give is, we lost InSight, we lost Spirit and Opportunity essentially to dusty solar arrays. Mars, Curiosity and Perseverance have our RTGs on them, and we just power right through dust storms. So, atmospheric opacity is another thing. When the dust is in the atmosphere, the sun dims, just like the wildfires cause it to be, less bright here. The dust on Mars can cause that to be a problem for solar arrays. So, I think that's some of the characteristics of the, difference between the moon and Mars that we'll have to deal with.
Oh, great. We have a question from Eric. I recognize you. Hi, Eric.
Hi. Thanks for this. This has been a fascinating panel. You mentioned several of the challenges of being so far from Earth, the distance that's involved, including the inability to evacuate and the communications lag. Another one is consumables and resupply, the logistics train that goes into it. One of the things that we've noted in the Human Health and Performance Directorate at NASA is the challenge of food and medicines. These things degrade over time, and oftentimes pre-positioning engineering materials or habitat materials is great for things that are not consumables, but oftentimes the lead time for pre-positioning makes it more likely for these things to go bad. So can you talk a little bit about how you see some of the challenges of the consumables, resupply, and logistics for this distance from Earth challenge, especially maybe with the cadence of things like Starship and stuff like that, where you don't have the value of pre-supply? Thank you.
Well, I definitely think there's I definitely think that there's opportunities to learn about how to produce food, on Mars and in transit, right? And there's been some experiments on space station, with everybody, talks about the lettuce and whatever, but I from what I've heard, having like a fresh vegetable or fruit, is a huge, so I think there's probably ways to combine, very stable, but maybe not super fun to eat things that are sustenance, where you can transport large quantities and store it, and combining that with some local food production to kind of keep people's spirits up. I think, again, this is where having a very large mass delivery capability, if you can land 100 tons of anything on the surface of Mars, it starts to open up what you can kind of conceive of in terms of infrastructure that you can use to produce lots of things, including food.
I have to say, as an analog astronaut myself, this is so exciting. That's such a great question. It's really a weight problem as well, because food requires water, and no matter how much you powder it, it doesn't taste good without water and texture. And we have NASA right now, as you shared in some of your slides, they have programs that I think they just announced the crew for Hera going in at JSC, which will have a whole year of a crew staying and studying exactly that with the food. And that's so important, because if we're going to go, everyone wants to go until they realize what they have to eat. We have another, and we have another great question. Go ahead.
Hello, everyone. Thank you all for the insightful, discussion. My name is Timothy T.J. Fidelis. I'm a graduate student at Howard. I have two questions. The first one is regarding taking human to Mars and beyond. Do you think those that are interested, like you said, the last speaker, every human has the opportunity to go to Mars one day? The second question is with respect to safety, especially during atmospheric re-entry. We launch a lot of, these spacecraft, and there are a lot of debris floating out there in the outer space. So I have not had any, effort towards how to, harvest some of these debris and ensure safety of a human during space flight. Thank you.
Thank you for your question. Can we really, all of us, go to Mars?
Oh, well, again, I don't think everybody's necessarily going to want to, but I think we would like to enable a future where anybody who wants to can. I think that is what will make us a multiplanetary species, which is a step in humanity as a species that I think is as important as a step relative to the future of our survival as just spreading out from Africa, where we first kind of evolved and then diversified and spread out all over the world. So I'm excited about it. I'm excited to be working on it. I think it's a matter of when, not if. I think your point on debris is a very good one. Space safety is very important. It's very important that we all are good stewards of the Earth orbit environment. Because there is no place in the solar system we can go without passing through Earth orbit first if we're leaving from Earth. And so taking care of that environment and making sure that we're responsible and aren't creating new debris and are responsible in the way we operate spacecraft and rockets is very, very important for that. You're, of course, always going to need some sort of shielding when you're flying through that environment because there's both natural debris and man-made debris that is too small to detect on any sort of, with any sort of, sensors. So you do have to shield against some of that, but we have the technology to do that.
Comments?
I think the shielding, or agree on the first point, it's not a matter of if, it'll just be when, if you want to go to Mars and can we all go to Mars, right? It's probably not something that happens, tomorrow. Which tomorrow it happens in is out there, right? And if you've got the willpower to want to go there, right? So it's not the easiest journey. And for the debris and the debris that's out there, like you said, the tracking is there, right? For the larger objects, but for the smaller things, it's more a risk posture as well as the design of the systems. So.
Yeah, and I think that the one thing to know about like coming and going is you transit that area of the high debris pretty rapidly as opposed to dwelling in it. We're seeing more evidence on station that, there are some more things happening that we do need to pay attention to. But if you're spending a lot of time in that area of low Earth orbit, that's a bigger problem for you than if you're just transiting it rapidly.
Another question? Go ahead.
Yeah. Thank you. I feel very privileged and happy to be here. I'm sure we all are. Thank you for that conversation. One subject I think wasn't talked about was artificial gravity. I wanted to know if there is any programs at NASA or SpaceX or the other agencies or companies that were mentioned that had any real program to study artificial gravity. Thank you.
There's obviously numerous studies on it, but right now it's not in the near term, at least the lunar architecture. I can't speak for Mars completely, but there's studies out there on what it takes to do that, but no real large efforts to actually implement anything in the foreseeable future.
I had a friend of mine who's an astronaut. I was asking him about artificial gravity and how important it is for going to Mars, and he said, "You're going to make me spend 6 months in space, and then you're going to take away the coolest part, which is getting to float around in zero G." So it's probably mixed opinions on.
We have another question here on the left.
Yes, hi. I'm Danette Allen. I'm the Senior Leader for Autonomous Systems at NASA. And I've heard the words autonomy and robotics, so you're singing my song. And I was just hoping to get your thoughts on, well, I take it as a given. We're going to need these things, right? For me, this is not a question. But what are your thoughts on test and evaluation of these systems, right? That must perform reliably, where we can't count on the humans to come in and creatively solve problems that we weren't expecting, right? The corner cases. Specifically, testing infrastructure. We don't have infrastructure right now to do this kind of testing. Standards, interoperability between NASA, the community, any aspect of the autonomy, the persistent autonomy and robotics challenge.
So, yeah, well, Danette, I think you and I need to talk more offline after this. So I agree. I think the autonomous systems have to be a big part of this. One of the things in the architecture and one of the tenets and the objectives is this interaction between humans and automated systems and robotics in general. Some of the things that we've come across in architecture is really what's the definition of all of these, right? We've got autonomy, teleoperations, telerobotics, remote operations, so there's a lot of different aspects of it. And I think one is understanding what are we really trying to do with each of those systems. And then if we really want to open this space, both the lunar and the Mars architectures up to everyone, we all have to kind of come to agreement that we're going to work together to achieve this, because as Bob mentioned, the budgets to achieve these lofty goals are going to be pretty astounding, right? And if we're all working in our little pockets, we're not going to get there in a comfortable manner. It's still going to be tough, but if we're more working together, it's going to be easier to achieve that than if we're all trying to work against each other and try to get to, this market share, this niche market. If we're working together, there's plenty of space out there and plenty of opportunities, as Nick mentioned. Each challenge comes with opportunities, maybe more than one. So I think for that aspect, if we're creative about it, we've done V&V on different systems, new systems, and obviously we're all hearing about artificial intelligence and all the advancements that are being made. And I think for us, we have to really look forward and embrace that and start thinking about how we do that ethically as well, and making sure that it not only allows safety, but sometimes, it may just be us, it may be the human that has to intervene. We may not be 100% reliable, as we see in certain autonomous systems nowadays that we use here on Earth. So.
I was just going to say, I think you've identified a great topic for a future Achieving Mars workshop.
Yes, thank you.
Okay.
So thank you very much to our
Segue
panel,
to
Dr.
Chris.
Fujimoto, Shatel. Thank you, Ben, Joe, and Nick. Let's give them a hand. Fantastic.
Thank you, Beth, and everybody. Fabulous panel.